So far, we have learned how to develop a histogram, and we also knew how to make it on Excel so that the process to develop a histogram will be much easier and straightforward. After we developed the histogram, this is not the end of the story, of course. We need to see um, uh, after we developed the histogram, we need to see what can we deduct from what we see in the histogram. So, so we will explore some key aspects when we look at any histogram. So the first is the shape of the distribution. Okay, so the first is the shape of the distribution. When we see a histogram, how does it look like? Okay, so from the shape of the histogram, we can explore what are the most common values and how great is the dispersion, meaning um, how far are we from the average of the performance. What is the distribution symmetrical? Is it skewed? By symmetrical, we mean that um, if we see the middle of the distribution, does the right hand side look uh, more or less the same as the left hand side? In this case, it is symmetrical. So this one looks symmetrical. This one doesn't look symmetrical. It's skewed, and this one also is skewed. This is a bit symmetrical, but it has multiple peaks, and by having multiple peaks, we can see that we have most of the performance either on the lower end or at the higher end. So if we see this example and compare it with relevance to the um, home appliances example, and if we say that the target number of years in terms of the livelihood of the product is 3 years, and we are actually averaging like when we see this distribution, and if we see that this is 3, it means that most of the devices are their lifetime are at 3, right? And we have deviation, we have dispersion to the right hand side and the left hand side, right? In this example, it means that most of the appliances are um, wearing out too early before the 3 years. This one looks like that our devices wears in most of the cases in after 3 years, which could be the good for your reputation. In this case, we can see that most of the devices are either before the 3 years, so most of your devices are wearing out after 2 years, or after 4 years, which is not also good for your business. Okay, it means that you have a high amount of dispersion. Okay, and this is the first thing that we can learn when we see any kind of histogram. Okay, so in other words, we can learn about the characteristics of our performance or our product's features and performance. So let's see one example. So we have here with actual numbers. See here an example with actual numbers. So in the previous slide, it was more or less to understand the concept, but here we have the actual numbers we got from our previous example about the thickness of the product. So here, what is the most common value? Okay, think of it. Okay, where is the most common value? So the most common value is the value with the highest frequency. So here we can know from looking at this histogram that most of our values are coming ranking. The top is from 3.47 until 3.51, and then the next most common value is 3.43, and then until 3.47, and then this is the third one in ranking in terms of commonality of values. So the most common value is 3.47 to 3.51. So what is the distribution shape? This shape looks like it is symmetrical, right? And it looks it resembles the bell curve. So the bell curve is what we call the normal distribution, because if you draw a line like this, you will see a kind of a bell curve in this shape. So the thing is that the third thing is seeing the shape of the distribution is the dispersion, right? Are all of our data in one area and there is no dispersion? No, there is some dispersion here. So we can see that most common values are, yes, around this area, but we also have some dispersion far from the average of the performance. Remember, so far we are not talking about the the target. We are talking just about our average performance and the dispersion. Okay, so the dispersion is between 3.3 until 3.68. This is the range. Isolated abnormal values are cases in which for example, you find values here and then values here and then no values between 3.55 and 3.6, and no values here as well, and then we find one value here. Okay, so that means that we have an isolated abnormal value. From this we can, for example, learn that we had an incident that is far from the normal performance and we need to investigate it, but in this case we don't have. So as we just mentioned, we have to compare, or we need also to compare our performance to the customer requirements. Okay, so let's look at this histogram again. Okay, so now we know from actual customer requirements that agreed with the customers, or the promises, that the specification limits are between 3.28 until 3.6. So this is the range through which the customer is willing to accept the products, right? And we can say, as long as we are within this range or the specification limits, we are in good hands. But in this case, we see that out of the 100 samples, we could see 3 cases are out of the specification limit. Okay, normally we will need to compare the our actual range, right? Actual range versus the acceptable range. Okay, so the actual range here is from 3.3 until 3.68, and the acceptable range is 3.28 until 3.6, and the actual average, so the actual average here is will be around this value, right? But the actual target, we will see about it, which would be the middle value between 3.6 and 3.28. We'll talk about this in a moment. So as we said, we are seeing that 3% of our samples, or our products, or our observations are out of the specification limits. Means that we have 3% out of specification limits. The average is 3.48. This is our average, right? And which falls between the 3.47 and 3.51, and the target is 3.44. Okay, so the customer requires us to hit 3.44. This is the optimum thickness, okay, or the optimum dimension. So in this case, we can judge that we are not, our average performance is not hitting the target, okay. So even that we do have a high dispersion, we are not able to, our average performance is not hitting the target, okay. And we have also 3% of our observations are out of the specification limits. So the third area to investigate, which is investigate and take actions. So first was to read the shape, okay. So discover the shape or identify the shape of the histogram. The second is to compare against the target values, and the third is that to investigate and take action. So based on your previous 2 points, you need to take an action, okay. So basically, as we said in the beginning, we can judge our performance by two parameters. The first is the average versus target, and also our dispersion versus the acceptable limits, okay, acceptable specification limits. So for example, in our case here, we have, like, for example here, if we compare our performance to the target, so here we have the customer requirement, for example the 3.44. In this case, we can see that our average performance is matching the customer requirements. Yes, we have dispersion, okay, but our average performance is hitting the target value, okay. Here we have the process is too high, which means that our average performance is way larger than or higher than the target value. And if we have this shape, so to the left of the target value, it means that we have our average performance is too low versus the customer requirements. This means that with looking at this, it means that we need to shift our average. We need to shift our performance in order to make sure that in the beginning we are hitting the target, okay. We are hitting the target in terms of the average, because this means that in most of the cases we are hitting the target, or our performance is around the target, okay. So here we answered the second question, which is, do we need to shift the average performance? In the first case, no. In the first case, yes, we need to shift it a bit to the left. In the third case, yes, we need to shift it a bit to the right, okay. Then we can see if we compare the dispersion of our performance versus the customer requirements, which are the lower specification limit and the upper specification limit. In the first case, we can see that all of our observations are within the customer specifications. So here we can judge that our process is within the requirements, or our performance is within the requirements. But here we can see that our process has very high dispersion, and we need to reduce the performance, reduce the dispersion using the other tools that we are going to learn about, okay. So this is basically how could we develop the histogram and then do it on Excel, and then investigate the shape of the histogram and compare it to the specification limits, and then take actions.
Welcome to our lecture online. Histograms can come in various shapes, not because we make them that way, it's just because the data drives those shapes. So they're so unique, those shapes, that we give them specific names. So when we hear the name, we understand what the data is shaped like. In other words, what the data then represents. For example, the first one here is called the normal, symmetrical, or triangular shape of a histogram. That is what we expect to see if the data is random and it's not skewed in any direction. In other words, we expect to see just as many high as low grades and many more in the middle. So this is what you would call a normal grade distribution, where the majority of the grades are in the middle, fewer at the high end and fewer are at the low end, and it's evenly distributed. For example, there's many A's as there are F's, and mostly there's C's, for example. That would be a good grade distribution. It would be what we call a normal, symmetrical, or triangular grade distribution. And so that's what we call the shape of that particular histogram. This is, of course, not something we would expect. We wouldn't expect to see just as many A's as C's as F's in a class. But if it was, then we would call that shape uniform or rectangular. It simply just means that there's the same number of each type of the data. What we sometimes also see that it tends to be skewed to the right. For example, here we see many more grades on the high end than what appears the most. Let's say that this was C's and we saw many more B's and A's instead of D's and F's. Or it could be skewed in the other direction, where we see very few A's, mostly B's, and then after that we see lots of C's, D's, and F's. So that means that in this case it's skewed to the high end, that means skewed to the right, or skewed to the low end, which means skewed to the left. Sometimes we see lots on one end and then it declines as we go to the right. In other words, we see mostly F's and D's and very few A's. In this case, we call it J-shape because it's kind of like the letter J. And then what sometimes happens, and I've had that happen in some of my classes, where it was bimodal, where we see lots of A's and B's, lots of F's and D's, and very few C's. That is obviously a problem. That means a big portion of the class was not understanding the material and it showed up in the test. So we want to do something about that. But again, it shows what we call a bimodal distribution, where we see not a central peak, but two peak offset with some data in between and some data on the sides. So those are the different kinds of data distributions that you could have, which then results in a specific histogram shape. And here are some of the major shapes that you may encounter.